Okay, let's record another 15 minutes to finish up this lecture on the rate of consolidation. Um, so so we have go through the three equations here, and you know how to calculate TV, UV, and UZ, and you based on the figure and table. Okay, so in next lecture we will actually talk about more examples in the calculation. But for this lecture, just know how to use the figure and table is enough. Um, so the CV is important parameter. Okay, CV is in this equation. Okay, to calculate TV, and CV is also called coefficient of consolidation. It's also in this governing equation, partial differential equation. So CV is actually the K in the consolidation calculation. So in laboratory test, we can directly calculate the CV. Okay, so I will go back to this slide later. Okay, it's kind of busy, but I go back to later. You will know what this slide means. So based on laboratory test, you actually can measure the time versus the deformation of source specimen. Okay, you can know that after you add load, you know the consolidation. This is a settlement of source specimen, and you know how long it will settle. This is based on one loading increment. What's that mean? So let's go back to our previous class. So this is our consolidation test. Okay, so let's say you add load. This is your initial void ratio. You add 3 kPa and your squeeze soil, your compressed soil. Okay, and your void ratio will decrease. It became E1. So this is 3 kPa. So, but it's not happen like instantaneously right after you add load. It takes time. Okay, so if you add the 3 kPa, you plot the settlement deformation versus time, you will have a curve like this. Okay, that's what this curve comes from. That is from each increment of load. And if you go back, you add another load, 5 kPa, you will have another curve like this. Okay, and you can continue to add, and you will have each of this load, it will have a time versus deformation curve. Okay, so that is this curve come from. If you plot deformation versus log time, you will have this shape. Okay, to determine CV, we need several steps. Step 1, you need to first plot deformation versus time. You have this shape. Step 2, determine D100. Okay, so at the end of the primary consolidation. So you have a large slope, small slope. You extend those two slopes and have intersection at A. Okay, at this intersection, you plot a horizontal line that gives you D100. That's second step. Third step is a little bit complicated. So along this axis, you need choose two times, T1 and T2. So and they have to satisfy T2 equals 4 times T1. Okay, that means if you based on how you select the T1, the T2. Okay, if you select T2, so your T1 is actually, let's say you select T2 here, your T1 will be around here. Okay, because T2 equals 4 times T1. And if you select T2 here, the T1 will be here. So it's a very subjective process. It's based on how you're gonna select the 2 points, but you have to satisfy this relationship. So once you have this relationship, you can extend those 2 lines, and you have intersection at B and C, and you plot 2 horizontal lines, and you have X. So the distance is X. Sorry, I plot. So you have the distance is X, okay? And you just you have this baseline, and you extend another x, you draw a horizontal line. Okay, that gives you D0. Okay, that's this step 3. Let's repeat this process again. You have 2 times, you can select any 2 times on the axis, but you have to satisfy T2 equal to 4 times T1. Okay, and you draw 2 lines. Let's remove this. You draw 2 lines, and you have intersection B and C. You draw 2 horizontal lines, give you X, and you just plot another X above B line, above this line. That gives you this line. Okay, and you have intersection between intersection which is D0. Okay. Now you have D0. Next, go to next step. You have D0, you have D100, and you just find the middle, D50, which is average. Okay, you have D50, you extend, you have intersection F, and you goes down, you have T50. Okay, the T50 actually is time for 50% average consolidation. Okay, let's go back. Let's go back one slide. Go back to several slide here. So if you look at this equation here, so T50 tells you 50% consolidation occur. The time for 50% consolidation. So U is 50% actually. Okay, and if you look at the figure here, so U is 50%, and you have TV equal to 0.97. Okay, so you know the TV equal to 0.97, and you know the T, you know DR. You can calculate CV. So that's the idea. That's what the equation shows. Okay, so you just CV equal to T50 HDR, capital T50, small T50. Okay, so T50 is 0.197. That's a 50% consolidation occur for time factor. HDR, that is the drainage. It depends on the soil specimen. If your soil specimen in a laboratory test is double drain, so your HDR will half of your thickness of soil specimen. If it's single drain, it will be whole length, whole height of soil specimen. T50 will be here. You read from this figure. So you can calculate the CR based on your laboratory test. And this is a method Casagrid proposed. Okay, and this is the first you measure T50, that is time for 50 average consolidation to occur. I can use this equation to calculate CV. This is a log time method. And if you look at the second, we have square root of time method. That is proposed by Taylor. It's another person proposed. So Taylor said instead of plot square root of time, you can plot, instead of plot log time, you can plot square root of time. And your time, your deformation versus square root of time will look like this. Okay? Go back one slide. This log time, you look like this. And square root time look like this. So first step, he said, find a point, okay, and draw a line, the tangent to the early readings, okay, around this area. So it's tangent to around this area. Again, it's very subjective. If you plot A here, if you say A is here, and your plot may be like this. Sorry. Yeah, it's very difficult to actually plot. So your plot may be like, remove again. your plot will be like this. Okay, so you know the idea. It's depend on where you select A and you go through a plot line tangent to this curve. Okay, so different people may select different point A will have different tangent curves. So that's where its subjective come from. And you find the point B, and you find the point C, which is OB. This is the important part. Once you find B, and your C will be 1.15 times OB. So it means OC equals 1.15 OB. Okay, you have point C here, and you just draw point C connect with your point A. A is the first point you defined, and you find the intersection, which is point D, and you have time here that gives you T90. Okay, so that's T90. Again, that tells you, okay, that is 90. The time for 90% consolidation occur. Okay, so based on the table, you can determine what is 90% consolidation occur for TV. That is 0.848. Okay, and it goes here. This is 0.848, and HDR T50. So that's T50 will be from here. HDR is based on laboratory test specimen, laboratory test condition. If double drain, you use half of a specimen height. If single drain, use whole specimen height. So that's the two method to calculate. The second method to calculate the consolidation coefficient. Okay. So finally, let's go to the settlement calculation estimation is very subjective process. Okay. If you compare your calculation with your field measurement, you can set up sensors in field and measure actual settlement of the building. If you compare the field settlement with your actual calculation, it could be, the error could be negative 20% or positive 200%. It's it's large range. So why? Because it's very difficult to calculate the pre-consolidation pressure. Very subjective in calculating CV. Like if you select the point A is different, your CV is different. Okay, so it's all have subjectivity in it, and also difficult to weather the sand layer is also difficult. We only calculate the clay settlement of clay layer, but the settlement of sand layer we didn't calculate. That's another source of error. And this consolidation theory has a lot of assumptions. At the beginning of the lecture, we say 6 assumptions to calculate in a calculation. So it's very subjective, and in actual field, the soil is more complicated. Okay, and those assumptions may not actually reflect the field condition. That's why I have a lot of errors. So this theory is just give you very crude estimation. If you want to know more accurate estimation, you have to take 460. That's foundation engineering class. That gives you more accurate calculation. That will be maybe some of you will take in next semester. So I will stop here, and this is the last slide. Again, I already talked about this. Sand layer, we didn't consider consolidation in sand layer in this lecture. Okay, we only consider consolidation in the clay layer. Okay, but sand layer provide a drainage path for the clay layer. If you have sand layer above or below clay layer, you have double drain. Water can go either up or down into sand layer. If you only have sand layer top of clay, you only have single drain, because water can only go up to sand layer. So let's stop here, and I thank you for your watching.